Okay, so we're going to talk about work. We've talked about work before, but this is a specific application of work that functions just a tiny bit differently. So this is work applied to a gas. Okay. Now, here we go. So here's the scenario. Imagine storing gas in a bag. And you want to know how much work does it take to make the bag bigger or smaller. Now imagine that the bag is stretchy. So consider the physics. Why does changing the volume require effort? If you have gas in a bag, why is it hard to make the bag smaller? Yeah, the gas is pushing back, exactly. Okay, so that's the work. So overcoming that effort of the gas, that's the work that we're finding. Okay. So how do we find it? Here we go. So now notice in this case, previously we said, actually, let me just explain. Okay. So in the case of a gas, force over area is called pressure. And this is newtons per meter squared. And once again, I think we've seen this before. So therefore, force equals pressure times area. Okay. So previously we learned that one way to define to define work is force times distance. So work equals force times distance, which is now, for a gas, is the same as pressure times area times distance. But what's area times distance?
Force. Volume.
Area times distance is volume. So in the situation of a gas, you can actually define work as pressure times volume. So W equals PV. Now we're going to do something that we haven't done before, which is we're going to think of work as a function of volume. So we can do this because we wrote it as an expression in terms of volume. All right. So if we take the derivative, we can write it like this. The derivative of work with respect to V is P. Or in other words, dW dV equals P.
Can you have work in terms of pressure as a function of pressure?
Yes. You can, so as you can see from this, anytime that you can write down something as an expression of something else, you can take the derivative with respect to any variable that you want. So, but what we're doing is we're taking derivative with respect to volume. Now, why is that? Well, given the scenario that I talked about at the beginning, what's the thing that's going to be changing? The volume. So in this particular instance, we want to think of volume as our variable. But certainly it's true in another scenario, you may want to think of pressure as the variable, as the thing that's changing. Or when you get to multivariable calculus, you may want to think of both of them as your variables, and you have two things that are changing. But so right now, like I said, we're going to talk about just this simple case. But yeah, it could be many different things. Okay, so from physics, in many situations, it's true that P times V is some constant. So if you want to know what P is, let's call that constant K. So therefore, if PV equals K, then P is just K divided by V. So what we have is that W prime is K divided by V, where K is a constant. So how do you find, so if we know the derivative of work, how do you find work? Take the antiderivative or the integral. So work is just the integral of K over V dV, and we say dV because we're treating V as our variable. And let me just make a comment. If you want to learn more about the physics of this, we talked about it informally. But if you want to learn more about the physics, look up the ideal gas law. And that's what this has to do with. Okay. So let's apply this relatively simple formula to a problem. Okay. So we have a container of gas. And let's say that because we know some physics or someone tells us PV equals 2. And so once again, we got dW dV equals P. So find the amount of work done as the volume changes from 7 cubic meters to 3 cubic meters. So what do we do?
We set up an integration.
Yeah. We know, let's see. So we know that work is going to be the integral of something. What is that?
From 7 m to the third to 3 m to the third.
Oh, okay. So this is, yes. Only when we write the calculation, we don't include the units.
I do,
But
for dimensional analysis.
oh, okay.
Work out.
Oh, okay. Personally, I check the units at the end.
Okay.
And now we're going to get something very strange and interesting here. We know we're starting at 7 and going to 3. Now we don't typically we don't have integrals that look like this, but it's simply a question of what's your starting value and what's your ending value. We're starting at 7, we're ending at 3, so it is what it is. Okay, now what are we integrating?
P dV.
Yeah, so we're going to integrate
P of V.
P dV. All right, well, what is P?
2 over V.
So P, since PV equals 2, then P is 2 over V. Okay. So what do we do if we want to integrate this? Yeah. Okay.
Make the V to the minus 1.
Okay.
The answer is 2 times ln of v.
1 over V. Will it be ln of V?
Okay. So it's 2 ln of V. 7 to 3. Wait, this can be...
The only thing work comes out is negative.
Yeah, that shouldn't be. Okay, so let me just say that for this integral, we need a negative in front.
Oh yeah, it's the definition. If you do it from A to B, it's the definition of an integral. If you're doing it from A to B, then it's a
Yeah, yeah.
positive. From B to A, it's
But
negative.
our A is 7.
I know.
Our B is 3. That's why
Okay.
it's not from
Oh.
So you get negative 2. So sorry, there should be a negative in front. Sorry about that. Okay. So negative 2 ln 3 minus negative 2 ln 7. And that... Okay. And that calculates to...
How did it become negative?
So. And by the way, since we're measuring work, what are the units of work? Units of work are joules. Next. Okay, so that was a simple physics application. Next, I want to come back and talk about a simple but important math application, which is to find the average value of a function. So we know what an average is. You just add up all the numbers and divide by n. But if you talk about the average value of a function, this is a little harder to talk about because you don't have n specific values. You've got, say, as x goes from 1 to 2, you've basically got all these values. So how do you find the average? So that's what I want to talk about right now. So suppose you have I'm just picking one example, the velocity function. Suppose you know the velocity function and you want to find the average velocity. How can we do this?
Calculate the contribution of each point. It's like the way mass works, the way we find mass. We find the contribution multiplied by the, well, in this case it would be y, and then divided by the total distance.
Yes, exactly. So to make that, to sort of go along that path more slowly, here first I want you to think of how could we do this as an approximation. So as an approximation, just take a velocity reading every so often, then add them up and divide by n. Does that make sense? Okay. So if you're driving for an hour, fine, take a reading every 2 minutes or something. And then that'll give you 30 readings, so then you divide by 30. And that should give you a good approximation of whatever your average velocity is. Okay. So just to write out an example, suppose here's our velocity function. 0.06 velocity is 0.06 t squared, where t goes from 0 to 10. Okay. So I'm now going to take 5 velocity readings. Yeah, because we're approximating. So, and here's the typical notation for this, little average. So our function is v, so v average is approximately, I take 5 readings. Velocity at 0, velocity at 2, velocity at 4, velocity at 6, velocity at 8. I figure out whatever those are, I add them up, and I divide by 5. Okay. So can you imagine what we're going to do in order to make this exact? Right. Because before we get to an integral, what's going to change? We're going to make n approach infinity. We're going to take more and more observations, and eventually that becomes an integral. You're exactly right. So now to make sure that we set up the integral correctly, let's point out how we got this set up. So, so we add up all the v values, and then we divide by 5. But where did 5 come from?
The number divided by.
Yeah. So 5 came from, there were that many values, but where did the number 5 actually come from? Well, we made some choices. The choices were, we're starting at 0, we're going to 10. So we've got a total length, or whatever distance, if you like, of 10 in our variable. And then we said we're going to take a reading every 2 seconds. So it's 10 divided by 2. So 2 is our delta t. Well, we don't want delta t in a fraction in a fraction. So we're going to straighten that out by flipping it to the numerator. So if you're in the bottom of a fraction in the denominator, that's just the same as being in the numerator directly. So it looks like this. Adding up all those t values, the sum of v of t, the delta t is just sitting there, and then that 10 minus 0 I'm writing as b minus a, but it's b minus a in the denominator. And when it's written like that, we now do the same thing we've done a million times before, which is if that's an approximation, we just turn it, in order to make it exact, we just turn it into an integral in the way that we've done before. So it looks like this. The average velocity is just 1 over b minus a times the integral from a to b of v of t dt. Now, I said velocity just because I felt like using an application, but everything that we've said you can do for any function. So, the average value of a function on a to b is just 1 over b minus a times integral from a to b of f of x dx. Now there's another way, there's another simple way to write this, which is actually the way that I like to write it, which is the following thing. The average value times b minus a equals the integral. I like writing it like that because I don't like fractions. And there's another reason which we're going to see in a minute. So, let's do this for real. Let's find the average value of this velocity function for t goes from 0 to 10. So what do? So v average equals what?
1 over 10 minus 0 times the integral from 0 to 10 of 16.
Yep. And this integral is just really straightforward now. So it's 1 over 10. The integral of that is 0.06 t cubed over 3, which is just 0.02 t cubed. And then we just evaluate it from 0 to 10. So when you plug in 10, well, here, like this, cube. And if you work this out, you get
20 times 2.
2. Okay. Okay. Now I violated my own rule. I forgot to give the units. So let me go back and give units. So velocity is meters per second, and time is in seconds. So if that's the average velocity, this is 2 meters per second. Okay. So I think this is a very, very simple, straightforward problem. Find the average value of any given function. Okay. So any questions on this? Okay. So, yeah. So what I'm going to show you right now is a little more conceptual, and so it requires a little bit of heavy thinking. And I'll just say the thing I'm about to show you is not your first priority, but it's sort of to enrich your understanding of what's going on here and the relationship between the different concepts. So, how can we think about what this calculation means? Well, one way to interpret it, I always like to do things graphically. So how can we interpret what's going on graphically? Well,
I was just saying, is this an average within a certain
Like
interval?
a one-dimensional
Okay.
average.
Yeah.
This is only the height of our function as it goes.
We're thinking about the height, exactly. So as you guys hopefully will recall, there's two different ways to graphically represent what an integral is. And we can interpret this average value formula in each of those contexts. So I'm going to do what I think is probably the easier one, which is integral as an area. So if integral is an area, then what does this formula tell us? So here's the picture. So I've graphed approximately the function itself. So if you graph the actual function, then the integral from a to b is just that area. And that's marked in green here. So then what is this other thing? Well, in this case, I'm using my second form of the equation, which is average value times b minus a equals the integral. So I'm saying something equals the area. What equals the area? Well, f average times b minus a. What do those two values represent? Well, that represents the dimensions of this rectangle in blue. The length is b minus a, starts at a, goes to b, so length is b minus a, and the height, I just drew it with the height of the average value, which was 2. And so what this formula tells us is that those two areas are the same. So what we're doing is we're constructing the rectangle that has the same area. So that's one way to interpret what average value means. And I like to think, if you think of this in terms of physics, I like to think of this in the following way. What if all that green stuff was water, and that water suddenly splashed down into a bin? What would it look like? It would look like that rectangle. Okay.
It's actually qualification.
Yeah?
To calculate if we have water like sitting somewhere.
So that's if you think of integral as area, and I think this is probably the simple graphical interpretation. I'm going to show you the other graphical interpretation. I think it requires a little more thinking. I want to show it to you anyway. Okay. So we said the other way to represent integrals is to think of the function that we're given as a derivative. Then you graph a slope field, and then the function is just a solution in that slope field. So what do we have here? Here's the slope field. So the slope field is velocity, and here's why I chose velocity, because we know it's the derivative of position. So I've graphed the slope field. So the slope field is determined by the formula 0.06 t squared. Okay. Now we said we're starting at t equals 0 and going to t equals 10. So I draw the solution from 0 to 10. And so that red curve is actually the function p, so the position function or the distance function. Okay. Well, one thing that we know is that if you integrate p prime, in other words, you're integrating the velocity, you get p of b minus p of a. Now I'm just going to divide both sides by b minus a. If I divide on the right side, I get this formula. And if I divide on the left side, I get p of b minus p of a over b minus a. That's just the slope between 2 points. But what we have on the right side is a formula, which is exactly what I just told you is the average value. So what does that mean? What that means is this formula tells you the slope between your starting point and your ending point. And this answers your question. So there are all these instantaneous velocities as you go along the position function. There's a velocity at 0, velocity at 1, velocity 2, velocity 3, da-da-da-da. But if you think about where you start and where you finish, you've got an average velocity for your entire trip, if you like. And this is how we find it. So again, these are two. So the formula for average value is very simple, but since there are two different ways of graphically representing integration itself, there's two different ways of interpreting what this means. And all just kind of really would depend on your problem, which one is more useful to you. Okay. So this was I would say a nice thought exercise. And if understanding this means you really, really understand the mathematics and what's actually going on and how to use it. So next I want to do what is a really, really crucial idea from physics. It's interesting. I'm going to have to teach you a little physics, and it's going to be a little bit hard. So in order to explain to you the physics, I'm going to sort of go on like a 5 or 10 minute journey just to explain some principles. So the center of mass, or centroid. So what is the center of mass of an object? It's the point at which that object is in perfect balance. So if you take something like a pencil, the where the balancing point or the center of mass is pretty obvious. It's just right in the middle. So that's obvious because there's just symmetry. But what if you have an irregularly shaped object? So, what if you have, let's see, I don't know, a mouse, like a computer mouse. Right. Computer mouse isn't that symmetrical. So where exactly is its quote unquote is its balancing point, which we're going to call the center of mass? I'm sorry? Exactly. So wherever there's like sort of more mass, the center of mass gets pulled in that direction. Okay. So what we're gonna do is we're gonna come up. We're gonna come up with a way based on our calculations to actually figure out what that is. So here's how we're gonna develop the formula. Okay, so to find this point, we must consider mass, but we must also consider position. So position is important. Think of a lighter person balancing a heavier person on a seesaw. Right? If the lighter person is further out, they can balance the heavier person. So you can't only think about mass, you have to think about both mass and position. Okay. Please. All right. So here is the formula behind the physics. In fact, considering mass and position, there's actually a very easy formula for that. So for a moment, just pretend that we only have two masses, so we don't have too much to think about. The system is in balance if the mass times the distance for the first object equals the mass times the distance for the second object, where I'm saying where m1, m2 are the masses, and d1, d2 distance. I'm measuring distance from the pivot point, which we could say is the center, but from the pivot point specifically. Okay. And let's see. So I go through a bit of a calculation here. I don't want to take you through every single step of the calculation. You can look at it at your leisure. But the main point I want to make is the following thing. If you want to set them in balance, I'm going to call x prime where the pivot point is. Now you could say the pivot point is 0, okay, but I'm going to say, let's pretend that we know where everything is. Where's the pivot point going to be? It could be at 1, could be at 2, could be at 3.7, et cetera, et cetera. So how do you find the value, the position of where that pivot point should be? Do this calculation, and you wind up with this. You have to add up m1x1 for the first object plus m2x2 for the second object, and then you have to divide actually by the total mass, by m1 plus m2. Now I did this for two objects. Can you guess, oh guess, what this will look like if you have more than two objects? Yes. Right. It's going to look like this. Okay. So the actual pivot point, which is called the center of mass or centroid, is found by dividing one thing by the other thing. What's that thing on top? What's that thing on the bottom? So first of all, that's the center of mass, as I said, or centroid. So that quantity on top is the notation is capital M, and it's called the moment of the system. This is physics terminology. Okay. And then on the bottom, when we add up all the masses, that's little m, that's just called the mass of the system. So what we know is we need to take the mass times the position for every object and add it all up, and then we need to add up the mass. That's going to give us the moment divided by the mass, which will be the centroid. Okay. This assumes that we have a list of a finite number of masses. But that we know in calculus that's not really what we're dealing with. And that's what we're going to look at right now. Okay. Centroid of a standard meter stick, obviously in the middle because of symmetry, as we said earlier. Okay. So now we're going to extend this to calculus, which we see coming because what's going to turn into what from our formula? Right now we have something that's going to turn into something else. You tell me.
I mean, both of them have exact values.
Yeah. This summation is going to turn into an integral. So let's see how that, but we don't have a delta in there yet. So let's see how this happens. Okay. So where is the centroid on a meter stick that gets heavier or wider the closer you get to the 1 meter end? So now we have an object that's not symmetric, so we can't just say it's in the middle. So clearly, since it's thicker at one end, the center of mass is going to be closer to that end. Okay. So let's have some formulas. Find the centroid for 1 meter stick, which has a width 0.1 x at the x distance mark. So, to find the center of mass, or the centroid, we need to find the moment and the mass, and then divide. So, first the mass, because it's simpler. What is mass? Well, the problem is we can't just add up a list of things because we have something that's continuous and not discrete, not a list. So we go back to using all our measurements. So mass is the same as mass divided by area times area. Okay. Well, mass over area is density. Okay. So let's assume that the material has constant density 2.4 kilograms per meter squared. Well, we know how to find area. It's an integral. Right. Think of your meter stick basically looks like this. And we define the area of that. We know how to do that. So, but we're not just finding the area, we're finding the density times the area, but the density is just 2.4, so we just stick the 2.4 in there. And so now we just have to calculate that integral. And we do it. Yeah. So after you use some simplification, you get 0.12, and it's mass, so it's kilograms. Next, we have to find the moment. So what's the moment? Well, moment was not just mass, but mass times position. So it's basically this, but times, well, what's the thing that represents the position?
X and Y.
Right, and which in this case, which variable? In this case, it's x. There you go. So moment is mass times position, but once again, it's the density times the area times the position. Right. So I filled in a couple extra steps here. But basically you wind up integrating the exact same thing, but because moment also includes position, we're also including x. This just shows how to break it down step by step. So here's the formula for moment, if you like. So, oops. There we go. We don't need mass. We don't need weight. Okay. So, yes. So it's the density, which is W, times the position, which is X, then times our quote-unquote area, but area just comes from the length, which is our function L of X, times our so-called width, which is just dx. And then you do that integral. Oh. So let's finish doing this. Which I neglected to do. Okay. So remember the notation for moment is m, which is the integral from 0 to 1, and that's 0.24 x squared dx. You do the integral, and you get 0.24 x cubed over 3, so that's 0.08 x cubed, excuse me, going from 0 to 1. So plug in 1, plug in 0, you're just going to get 0.08 as the result. So that's the moment. Now if we want to find the centroid, what do we do? The centroid is
Moment divided by
moment divided by mass. So big M for moment, little m for mass. So the moment was 0.08. The mass was 0.12. So centroid is at the 2/3 mark. And since centroid is measuring a distance or position, this is in meters. So to briefly summarize, in order to find the centroid, you need to find the moment and find the mass and divide. How do you find the moment? You do density times position, which is x, times the length function L of x dx, integrate that, and that's the moment. To find the mass, same thing but erase the x. You do the density, here we go. You do the density times your length function times dx, and then you integrate that. Okay. So a couple comments. What if here I said the density is some constant 2.4? What if the density varies? What if in some cases the material is heavier, some cases it's lighter? What do you do?
Separate integration.
No.
you use density.
Just stick it in the formula. Instead of W being a number, W is a function. Big deal. So then we integrate that with it.
And then you can also change it to y.
These calculations find the x-coordinate of the centroid. What if you want to find the y-coordinate of the centroid? No problem. Just set it up dy. Okay. So let me make a comment about that. the way I'm going to talk about doing the calculation is setting it up as a function of y and then doing the calculation dy. So it'll look exactly like that. If you look in the textbook, there's a fancy formula, and I just want to do it this straightforward way. Okay. So let's look at an example. Another example. Find the centroid of the region bounded by these two graphs, y equals x and y equals x squared, with density 12. So what do we have to do? In order to
Find the boundaries.
find the boundaries. Okay.
Just pause it.
Good point. So, actually, let me do this. What? Okay. There we go. Okay, so it's true. We know we're going to do some integrals. We're going to need to know what the actual region is. So what's the actual region? So y equals x looks like this. Y equals x squared. Simple parabola looks like that. Okay, what are the 2 points of intersection?
0 or
X equals 0. And can you guess what the other point of intersection is? Yeah, x equals 1. Normally you'd have to set them equal to each other and solve it, but I made this simple on purpose. Okay. All right. So now what? Now, in terms of the physics and the setup of the problem, what do we have to find?
We have to find the mass.
We have to find the mass, exactly.
And then find the start.
We have to find the mass and the moment. Now, how do we find the mass?
integrate
You put the integral.
the 1 minus the other
Density.
one with the
Right.
density together.
Right.
times-
So we're going to... Okay. So we're going to take the integral of the density, which is 12, times what?
Like
Well,
that. Fy, yeah.
We can choose, let's say, integrate over
That
the
takes
x
six.
Yeah.
from 0
Let's...
to
Yeah, we're going to go... Everything's already written with x as a variable, so we're just going to do this dx. So it's going to be the density times what? Times the function dx. But now what's the function?
the function is going to be x minus x squared because x
Yeah.
is 9.
Exactly. So it's not just the function, it's really the length function. Well, what's the length function? The length function is whatever, at a particular x value, whatever the length is. So what's the length at a particular x value? It's the distance between those two functions.
That'd be x squared.
So you can see that the x is on top and x squared is on bottom. So as we've seen before, you want to do x minus x squared. Okay. And we know that we're integrating from 0 to 1. So this will give you the mass, which we need, so that's good. Okay. Call the mass little m. All right. Anyway, you do calculation and you get 2. Oh, and by the way, 2 what? 2 bananas? It's a mass, so it's 2 kilograms. Okay. So now what do we need to find?
Moment.
We need to find the moment. How do we do that?
The density.
Okay.
And the length.
Basically do the exact same integral, but what's missing?
The multiplication of x.
The multiplication of x, because it's not just, because moment isn't just mass, it's mass times position. So we're going to have to put an x in there. But as we find this moment, which moment are we currently finding?
dx.
We're finding the moment for the in the x direction. How many different moments are we going to need to find?
Two. X there.
We're going to need to find one for x and one for y, because at the end of the day, when we say what the center of mass is, how many different values do we need to give? How many different numbers? 2. This is a two-dimensional object. So it's good. So the center of mass, the balancing point, is going to be a point in the plane. So you're going to need an x variable and a y variable, or x coordinate and a y coordinate rather. So let's do the x moment. So the x moment is, like we said, 12 times x minus x squared dx, and we're going to integrate from 0 to 1. That should be from 0 to 1, but okay. Okay. So we do that calculation, and we get 1. Okay.
Did you skip step in there? Shouldn't be x squared over 2?
Where?
12?
Oh, here? I distributed.
No.
Over here?
Next one, yes, right there, the middle.
Oh, it's 2x over 2 minus 3,
X
x
over three.
cubed over 3. It's not just 2 square minus 2.
But then the answer is right.
Oh.
Substitution is right.
No, it's one step below. We're reading.
Yeah.
Yeah,
Sorry. Typing issue. Yes. I forgot that. Okay. Okay. So we have the mass and we have the x moment. Well, now we have the x moment and the mass, so now we can find the x part of the centroid. Just do the moment divided by the mass, the x coordinate for the centroid, which I just call the x centroid, is 1/2. Okay? Now we also have to find the y. So how do we do that?
Same thing, but we have to set it up the whole thing in terms of y.
You have to set up the whole thing with y as your variable. So how do you set this up with y as your variable?
We write the formulas,
Yeah.
then subtract. Now we're going to be subtracting the opposite, the one from
Right.
the other, because that one is on top of it.
Right. So first of all, since we're setting this all up in terms of y, y equals x, well that's pretty easy. We'll just write x equals y. But y equals x squared, we want to make y our variable. So now x equals the square root of y. But now we've got our functions, and now we just do everything the way that we want to do it with y as our variable. So the y moment is the integral of the density 12 times the position, which is now y, because we're talking about y. Times the top function minus the bottom function. But in terms of y values, look at the picture. Which one's on top and which one's on bottom? If you think in terms of yeah. If you think in terms of dy, what was the parabola, which we're now thinking of the square root function, is the one on top. And y equals x, or x equals y, is now on bottom.
I don't get it.
Rotate this whole thing to the side. Like, flip it like 90 degrees like that.
If this is so this is our dy piece.
Counterclockwise.
So if you think of it in terms of
That thing is on.
dx, which one has the bigger value, which one has the smaller value? The one that's bigger is the y equals x. The one that's smaller is y equals x squared. When we say bigger and smaller, we mean a bigger or smaller function value or y value. But now, operate dy, and we're saying which one has a bigger value, but if y is our variable, we're saying which one has a bigger x value. So now the bigger x value is the parabola. So that's the one that's quote unquote on top. Okay. So just do some algebra, then do the integral. And also we now need to know our y boundaries. So when x equals 0, what's the y value? 0. When x equals 1, what's the y value? 1. Oh, just by coincidence, it's the same numbers. So we do that, evaluate it from 0 to 1. You work it out, and you get the y moment is 4/5. So then we now need to find the y centroid, the moment divided by the mass, which is 2/5. So we now have the x coordinate and the y coordinate. So finally we can say that the center of mass is that, 0.5, 0.4. So in other words, if we, so let's see, so 0.5 is probably about there, 0.4 is maybe about there. So there you go. So if we had something of that shape and we stuck our finger at that point and just let it go, it would balance on that point. That's what your center of mass means.
We can do 3D out of this.
You can just add another dimension.
You could.
You can do it in vector form.
Oh, yeah, kind of.
We did it in
Um,
vector.
Okay. So, any questions?